Good morning. Today we'll start with the third chapter, fuel air cycles and their analysis. In the previous chapter, the previous videos, we had discussed about the auto diesel and dual cycle with air standard cycles. We had assumed only air, but in the actual cycle, along with the air, we had fuel. So we will start with the actual cycles with fuel, air cycles and their analysis. So we will start with introduction. In this chapter, a detailed discussion of air standard cycles, particularly for IC engines, has been given. The analysis was based on highly simplified assumptions. Because of this, the estimated engine performance by air standard cycle analysis is on the higher side compared to the actual performance. You can see the air standard cycle which we had done in the previous chapter. They will show the higher efficiency and higher performance as compared to the actual engines. We will take an example here. The actually indicated thermal efficiency of an spark ignition engine with compression ratio 8 to 1 is found to be 28%, but the air standard efficiency is 56.5%. So you can see here the actual efficiency of SI engine is almost half the air standard efficiency of SI engine. So this large deviation may to some extent be attributed to progressive burning of fuel, because in air standard cycles we assume that there is only air. Apart from that we had their number of assumptions, but in actual cycle we had burning fuel. Okay, we had air fuel mixture will come into cylinder, and after combustion we had burned fuel. Okay, incomplete combustion is also a factor. Whole air fuel mixture won't burn, some part will burn and some part will remain as unburnt. And you can see valve operation, because in actual engines valve will take some time. In air standard cycles what we assume that valve will open instantaneously, but in actual engines valve will take some time. There is a friction factor also, lag also. However, the main reasons for this may be attributed to the oversimplified assumptions made in the analysis. As mentioned here, in the air standard cycle, the assumptions are very simple, but in the actual case, it is not so. In an actual engine, the working fluid is a mixture of air, fuel, vapor, and residual gases from the previous cycle. Further, the specific heats of the working fluid are not constant but increase with temperature. Specific heats like Cp, heat addition at constant pressure, like Cv, heat addition at constant volume, they will change with temperature. Lot of things will change with temperature. Like if you take the example of a iron piece, metal piece, it will expand with temperature. Its properties won't same. Its strength will not remain same. Same here, specific heats will vary with the temperature. But in the air standard cycle, we had considered that the specific heats are fixed. Same. Finally, the products of combustions are subjected to certain dissociation at high temperatures. When there are chemical reactions, there are products. The products are subjected to dissociation at high temperature. If the actual physical properties of the gases in the cylinder before and after our combustion are taken into account, reasonably close values of the actual pressures and temperatures existing within the engine cylinder can be estimated. The mean effective pressure and efficiencies calculated by this analysis in the case of well-designed engines are higher only by a few percent from the actual values obtained by test. The analysis based on the actual properties of working medium, fuel and air is called fuel air cycle. You can say the actual analysis where we consider fuel, air and its varying properties. All the properties of gases will change. That is called fuel air cycle analysis. And even this analysis has simplifying assumptions. However, they are more justifiable and close to actual conditions than those used in air standard cycles. Whatever we had assumed in air standard cycle is not any near to the actual engine conditions. But whatever we use in fuel air cycles, that is very near to the actual engine conditions. So this part is introduction of air fuel cycles.